What specific problem does ENIGMATA aim to solve in the context of existing large reasoning models, LRMs, and their challenges with purely logical reasoning tasks?
ENIGMATA aims to address the limitations of existing large reasoning models, LRMs, that struggle with purely logical reasoning tasks, particularly in solving diverse puzzle types that require logical skills rather than specialized knowledge. Current LRMs often focus on benchmarks for evaluation, without providing adequate training methods or resources to tackle these challenges effectively. ENIGMATA introduces a comprehensive suite that includes a scalable and controllable puzzle dataset, ENIGMATA Data, which features 36 task types across 7 categories, allowing for automatic generation and verification of puzzles. This dataset is designed to enhance the training of LLMs through the reinforcement learning with verifiable rewards (RLVR) paradigm, enabling models to develop strong puzzle-solving abilities. By providing a diverse and challenging set of verifiable prompts, ENIGMATA facilitates the systematic training of LLMs to improve their logical reasoning capabilities, thereby filling a critical gap in the current landscape of reasoning models.
How does the proposed ENIGMATA method or algorithm work? Please illustrate it step by step, including details about the data construction, training methodology, and evaluative components.
The ENIGMATA method operates through a structured approach that encompasses data construction, training methodology, and evaluation components. First, the data construction involves 3 phases. 1. Tasks collection and design, where 36 logic puzzle tasks are curated, with 30 tasks featuring scalable auto-generators for additional instances. 2. Auto-generator and verifier development, which equips tasks with generators that create puzzles and verifiers that validate solutions. And 3. Sliding difficulty control, where key variables are identified to adjust puzzle difficulty levels. Next, the training methodology consists of a 2-stage process. 1. Rejection fine-tuning, RFT, which establishes foundational reasoning patterns by combining puzzles with mathematical problems to ensure a balanced reasoning development. And 2. Multitask reinforcement learning, RL, which employs mixed training RL to integrate multiple puzzle types and multi-stage RL to build core skills progressively. This dual approach enhances generalization and prevents overfitting to specific problem types. Finally, the evaluative component is embodied in the ENIGMATA eval benchmark, which rigorously assesses the model's reasoning capabilities across diverse puzzle instances, ensuring no data leakage between training and evaluation sets. The combination of these elements allows ENIGMATA to effectively train LLMs to solve complex reasoning tasks while maintaining robust performance across various benchmarks.
Can you provide a simple yet illustrative example of how the auto-generator works within the ENIGMATA data suite, including an example of a generated puzzle and its subsequent verification?
The auto-generator within the ENIGMATA data suite operates by creating scalable puzzle instances tailored to enhance logical reasoning capabilities. For instance, in the arithmetic puzzle category, the auto-generator might produce a puzzle like, what is the result of 7 plus 5 to 3? This generated puzzle is then verified by the corresponding auto-verifier, which checks the model's output against the correct answer, in this case 9. The verifier instantly assesses the response as correct or incorrect, providing immediate feedback that can be used to assign rewards in the reinforcement learning with verifiable rewards, RLVR framework. This automated process allows for the generation of unlimited self-verifying puzzle prompts, facilitating extensive training and evaluation of models on diverse reasoning tasks.
What are the theoretical or practical benefits of using the ENIGMATA method, particularly in terms of scalability, controllable difficulty, and its integration into reinforcement learning?
The ENIGMATA method offers significant theoretical and practical benefits, particularly in scalability and controllable difficulty, which are crucial for effective reinforcement learning, RL integration. Firstly, ENIGMATA data features 36 task types across 7 categories, allowing for unlimited self-verifying puzzle prompts that can be generated at varying difficulty levels, thus supporting extensive scalability in training datasets. Secondly, the programmatic difficulty control enables researchers to mix puzzles in desired ratios, facilitating fine-grained experiments on how different difficulty levels influence RL outcomes. This adaptability is essential for developing robust models capable of generalizing across diverse reasoning tasks. Additionally, the automated verification system ensures that the generated puzzles are instantly checked for correctness, streamlining the RL training process and enhancing the overall efficiency of the model's learning. Overall, ENIGMATA's design not only addresses the gaps in existing puzzle datasets, but also provides a comprehensive framework for training LLMs with advanced logical reasoning capabilities.
How is the ENIGMATA approach validated or tested? Discuss the experimental design, datasets used, and the benchmarks or metrics for evaluating the performance of the developed models.
The ENIGMATA approach is validated through a systematic experimental design that includes the use of diverse reasoning benchmarks, such as ENIGMATA eval and the challenging ARC-AGI benchmarks. The dataset comprises 4,758 puzzle instances sampled from ENIGMATA data, ensuring a rigorous evaluation of logical reasoning capabilities across 3 difficulty levels: easy, medium, hard. Performance metrics include the PASIT-K metric for evaluating model outputs, with models being trained on a balanced mix of puzzle and mathematical problems to enhance generalization. Additionally, the models are assessed on out-of-domain (OOD) benchmarks to evaluate their reasoning capabilities beyond the training data. The results indicate that the models trained with the ENIGMATA approach outperform existing state-of-the-art models, demonstrating the effectiveness of the dataset and training methodology.
What specific results were achieved with the ENIGMATA method in terms of model performance on benchmarks like ENIGMATA eval or ARC-AGI, and how do these results compare to existing state-of-the-art models?
The ENIGMATA method significantly improved model performance on benchmarks such as ENIGMATA eval and ARC-AGI. Specifically, the model Quen2, 5-32b ENIGMATA outperformed most public models on ENIGMATA eval, demonstrating the effectiveness of the ENIGMATA dataset and training recipe. Additionally, it surpassed strong reasoning models like Gemini 2, 5 Pro and O3 Mini on the challenging ARC-AGI benchmark. The training strategies employed, including rejection fine-tuning and multitask reinforcement learning, yielded substantial performance gains on out-of-domain benchmarks, indicating enhanced general logic reasoning abilities. Overall, the results suggest that the ENIGMATA method not only excels in puzzle reasoning, but also contributes to improved performance in broader reasoning tasks, showcasing its potential as a free lunch for expanding reasoning capabilities in LLMs.